Hello everyone, welcome to this course on CFD modeling using ANSYS CFX. This is a course by LearnCAx. This particular session is part of that course, and in this particular session we are going to see a CFX case study. This is a simulation which is carried out for modeling flow through a duct bend, and we will see the effect of guide vanes. In this particular problem, we are going to keep the flow the fluid flow in the low turbulence regime. We are going to see a low turbulence case without guide vane first, and then we will see a low turbulence case with guide vanes. We are going to see the entire problem definition, simulation setup, and how to extract results and compare results in the two cases in this particular session or case study. So first we have a duct bend geometry. We will be walking through the entire analysis of a simple problem, that is the flow through a duct bend. The mesh is already generated. We won't go into details of generating mesh. We have used standard ICM CFD tool for generating the mesh. We will import the mesh into CFX pre, set up the physics, run the solver from CFX solver manager, and then see the results in CFD post. After completing this first simulation, we will add two guide vanes into the next simulation. We will turn on the heat transfer model and run the simulation again and compare the results. The problem definition has fluid as air at 25 degrees centigrade. The inlet speed is 0.1 meter per second, and this corresponds to about 3000 Reynolds number, which is low turbulence and transitional flow regime. Outlet is opening with flow direction being normal and relative pressure of 0 pascals, and the backflow intensity is used as 2.5% turbulent intensity. To set up this model, we will need to import the mesh, define the computational domain, set the boundary conditions of inlet, outlet, and symmetry, set the initial conditions, and define the solver parameters. Let us continue to see this case study. First, before starting CFX, make a folder in the D or E drive with your name and set this as the working directory. Then start CFX pre from CFX launcher or command prompt. After that, import mesh into the CFX pre. We will start a new simulation, select the general mode option, save the simulation as duct bend 2. We will import the mesh duct_bend_mesh.gtm, and we will expand the tree to see the 2D and 3D regions that are there in this particular mesh. So these are the different default domains that are present in the geometry. There are two 3D regions. Let us see what domain are present in the CFD problem. We double click on domain definition. We do not change the basic settings. We will only see the materials and locations. Then we click on fluid models and turn off the heat transfer equation. We will select none in the heat transfer option. Turbulent option is SST K omega. We also activate the transitional turbulence and the gamma theta model. We click OK after this. Then we go to boundary conditions. We create the inlet boundary condition. We set the type as inlet and select the surface. We set the flow as 0.1 meter per second. Turbulence should be set to low intensity. We create an opening for the outlet. We select the surface in that. We also set the outlet turbulent intensity, backflow turbulent intensity. We define separate symmetry boundary conditions, symmetry 1 and symmetry 2. All remaining external surfaces will have this default boundary condition of no slip, which is all clubbed together in the default domain default boundary condition. We have not created any internal boundary conditions, so the flow will not see the turning vanes and pass straight through them. So this is how the boundary condition looks like. First we have an inlet, then we have an outlet, and the symmetry conditions. After this, we initialize the flow by clicking on the initialization icon. There are two options. Automatic will use existing solution variables, otherwise the solver will generate an initial guess. Automatic with value requires a value. For versions lower than 12.0, check the turbulence eddy dissipation box. Set the turbulence option to low intensity and eddy viscosity. Leave all the options set to automatic for this case. We will leave all options to automatic for this case. As a first case, the solver will make some simple intelligent calculations, assumptions to get things moving. Too many details to discuss here, but we will write a backup file before the first iteration to see the initial guess. Now the solver will control, that is, what type of solver settings are required. We define the solver controls advection scheme as high resolution. We define the turbulence numerics as high resolution as well. Then we set the auto time scale, maximum number of iterations is 300, and length scale option is turned to conservative, that is lower length scale option. So convergence criteria we set it to 1e-5, which is the stricter convergence criteria. We start the solver by clicking on the define run icon. In the solver, we have to start the run. Once the residual plots appear, we have to switch between RMS and maximum value. We create new monitor plots and monitor the imbalances as well. For this, we go to flow outlet, P mass flow. We see the mass imbalance, and when the run is finished, we see the results by clicking on the results icon. In CFD post, we select different post-processing entities like objects, planes, locators, contours, and we display the contours of pressure. In the pressure contours, we are seeing this particular pressure contour on the plane, which is at z equal to 0.05. We also plot vectors on the same plane. Now we try. You can also try out other features similar to the earlier case study of plotting streamlines and contours. Now we will run another case with guide vanes and heat transfer to compare our results with the earlier case. In this case, we will run the same case, but we will now rerun this case with heat transfer on and two guide vanes or turning vanes. To do so, we need to modify the domain settings, add boundary conditions for the vanes. Since the heat transfer model requires more information at some of the boundaries that we have currently defined, changing the model will cause inconsistencies in the definitions of these boundary conditions. These will appear in red in the object selector with a corresponding explanation in the physics error summary. What we can do is, we may correct these automatically by right-clicking on the red text and selecting Autofix Physics, thus taking the defaults. In other cases, a value may be required. Duct bend with vanes. For this particular case, we are going to use the working fluid as air at 25 degrees centigrade. Inlet speed remains same, 0.1 meter per second. Inlet temperature is 300 Kelvin. Outlet is an opening with flow direction being normal and relative pressure 0 pascals. To modify this model, we will need to modify the domain models, modify the inlet boundary condition, create boundary condition for the vanes, and modify the initial conditions. To edit domain, if we have exited CFX pre, we launch CFX pre again and open the existing simulation. We edit the existing simulation, that is default boundary of default domain. We change the heat transfer model to thermal energy and click on OK. After this, we edit the boundary conditions of inlet. In that case, wherever the red option was there, which means we have to change the boundary conditions. In the inlet boundary condition, we change the static temperature to 300, and also in the outlet boundary condition, we change the static temperature as 300. That is a reverse flow temperature. Now we introduce guide vanes. We create a boundary condition for the first vane, vane 1. We set the boundary type as wall and location as vane 1. And for temperature, we set it as 350. For the second vane also, we repeat the same settings. There is no SIP wall and temperature is 350 Kelvin. We write the solver file again after this. We start solver. When prompted on solver manager, we start CFD post and shut down the CFX solver when the simulation has converged. We load the previous CFX post state by importing the file duct_bend.cst into CFD post. The objects and plots that we previously created for the case without duct vane will now be updated with the new results with duct vane. We examine the existing objects to see the effects of turning vanes in CFD post. On the comparative study can be performed by loading previous results as well, so that both the cases appear side by side. For that, we go to File, Load Results. Under Case option, we activate Keep Current Cases Loaded so that both files are open simultaneously. We choose the earlier file, which was duct_bend_001.results, and we click open. So this is the comparison of the two results. The left one shows with guide vanes, the right one shows without guide vanes. As you can see, the flow separation is drastically reduced with guide vanes. We have more uniform flow going through each vane section, and this particular high velocity spot is reduced. When we see on pressure, this high pressure spot is drastically reduced, so this improves stability of the structure as well. And this flow separation is also reduced when we introduce the guide vanes. Due to low turbulence, it is visible that in absence of guide vanes, there is a recirculation zone where there is flow reversal. The velocity profile is now compared, and you can see the red is for the case without guide vane, and it has reverse flow. Whereas with guide vanes, the profile is now much more uniform, which is the blue profile. So thank you for attending this particular session on case study of low turbulent flow with and without guide vanes in a duct bend. I hope that was useful for you in order to study how to set up a case in ANSYS CFX. See you in the next session of the CFX course. Thank you.